Hello everyone, welcome to my channel. Today we're going to look at two common matrix operations, the matrix multiplication and the matrix inversion. We know that finding the inverse of a matrix is much more complicated than finding the product of two matrices. But it turns out that the two operations have the same computational complexity. What I mean by that is that if there's an algorithm for matrix multiplication, then there must also be an algorithm of the same complexity for matrix inversion. And vice versa, if there is an algorithm for matrix inversion, then there must also be an algorithm of the same complexity for matrix multiplication. Let's first show the easier direction of it. Suppose that we already have an algorithm for finding the inverse of an n by n matrix, and the complexity is n to the power a. And we use in for the number of operations needed for that. So in is less than or equal to a constant c times n to the power a. What we need to do now is to find an algorithm for finding the product of two n by n matrices. Say A and B are two n by n matrices. This is what we're going to do. We first find the inverse of this augmented matrix, and then we just take this block in the top right corner. That gives you the product of A and B. So the number of operations needed for that, for calculating AB, Pn is equal to I3n, because to find AB we just need to find the inverse of this bigger matrix. And I3n is less than or equal to c times 3n to the power a, and that has complexity of order n to the power a. Now let's prove the other direction. Suppose we already have an algorithm for matrix multiplication and the complexity is n to the power a. We need to define a new algorithm for matrix inversion whose complexity is the same. Let's see how do we do that. We're going to define this new algorithm in an iterative way. Let's say I of n is the number of operations needed to find the inverse of a n by n matrix using this algorithm. And firstly, I of 1 is equal to 1. And this is because when n is equal to 1, we have a matrix whose dimension is 1. So there's only one element in the matrix. And to find the inverse of this matrix, the inverse of this matrix is simply the matrix whose element is 1 over x. So we only need one division to find the inverse of this matrix. So the number of operations is 1. Next, let's suppose we already know how to find the inverse of a matrix whose dimension is n. And we are given a matrix whose dimension is 2n. So how do we find the inverse of that? We first break it up into 4 submatrices, where each submatrix is of dimension n. And suppose this is invertible, so the determinant of this matrix is not 0. And we can assume that the submatrix A is invertible. If it's not, we can use elementary row operations to make it invertible. So without loss of generality, we can assume that A is invertible. And if A is invertible, we can show that the determinant of this matrix is equal to the determinant of A times the determinant of D minus CA inverse B. Because A is invertible, so this is not 0, and we know that this product is not equal to 0, so the determinant of this D minus CA inverse B is not 0. So D minus CA inverse B is invertible. And we call that delta. This is invertible. And then we're able to show that the inverse of this matrix is given by this formula. This is a well-known result in linear algebra. The way to show that is by using elementary row operations. So you first augment this matrix by stacking a identity matrix to the left of it, and then you perform some row operations to make this matrix the identity matrix, and then the identity matrix becomes the inverse of that matrix. And because we assumed that we already know how to calculate the inverse of a n-dimensional matrix in our iterative definition of the algorithm, so we're able to use this formula to get the inverse of the bigger matrix, because we just need to get the A inverse and delta inverse, and A and delta are both of dimension n. And now let's find the number of operations needed to do this. First of all, we need to get A inverse, and the number of operations needed is I of n. And then we need to calculate delta, which is D minus CA inverse B. So we only need 2 matrix multiplications. Remember, in the calculation of number of operations, we only count multiplications and divisions. We don't count additions or subtraction. So the number of operations is 2pn. Remember, pn is the number of operations needed to find the product of 2 n by n matrices. And next, we need to find delta inverse. Again, that's I of n number. The number of operations is I of n, and we need to find the product. So we need 1, 2, 3, 4. We need 4 matrix multiplications, and to get this, we need 2 matrix multiplications, and to get that one, we need another 2 matrix multiplications. We're actually overcounting the number of operations, because if you see that CA inverse and CA inverse, these two are common elements, so we don't actually need all of these, and adding them up gives you 2in plus 10pn. So I of 2n, which is the number of operations needed to find the inverse of this bigger matrix, is less than or equal to 2i plus 10p. This iterative process will give us algorithms to find the inverse of matrices whose dimensions are 1, 2, 4, 8, or in general 2 to the power k, where k is any non-negative integer. You might wonder, what if we have a matrix whose dimension is not of this form, say a 3 by 3 matrix? What we can do is that we can embed such a matrix in a bigger matrix whose dimension is of this form. Say if A is 3 by 3, then we can add a single 1 here to make it 4 by 4. And the inverse of this matrix is A inverse, and everything else is the same. So we just take this part that gives you the inverse of the original matrix. So without loss of generality, we can only consider the case when n is k to the power 2 to the power k. Now we use this inequality repeatedly to show the complexity of our algorithm. Suppose n is 2 to the power k. So using that inequality, I of 2k is less than or equal to this. And then we use the same inequality for this I. And then we have this thing is less than or equal to this. And then we repeatedly use the inequality for I. And then we end up with this. Okay, And then because I of 1 is equal to 1, we've already shown that before. And then p of 2i is less than or equal to a constant times 2 to the power I to the power a. And now we use the basic algebra for geometric sequence. And also notice here that we have already assumed that a is greater than or equal to 2. So eventually we're able to show that the complexity is of order n to the power a.